Okay, may I have your attention, please? Okay, so today is our third showcase, IMO showcase. We have two speakers today. The first one is our academic director, Cezar Lupu. Let's welcome.
So, I hope you can hear me well. So today I will talk about an algebra problem. So this was problem 2. It's an older problem though, at IMO in 2001. And I'm going to tell you a bit of a history about this problem. And let me start with the statement first. So it says that, show that for any positive reals A, B, C, we have the following inequality. So the inequality is as follows. It's the sum, I'm going to write it like this, of A over the square root of A squared plus 8BC is greater or equal than 1. So probably most of you know this problem, and you have seen it numerous times. But this problem, although it looks easier now, at that moment was considered one of the hardest. And although it was chosen to be problem 2, based on the points that each team got, well, I'm just going to refer to the points that Romanian team obtained on this problem. So the Romanian team got only 10 points, all of them, on this problem. It was by far the hardest problem for the team. And not just for the Romanian team, but also for other teams as well. Well, meanwhile, after some time, there have been many generalizations of this problem, many approaches. And today, I would like to show you a couple of those. I would like to show how we can use classical inequalities to prove this problem. And we will see that we can approach this in various ways. We can use, like I said, the classical inequalities like Cauchy-Schwarz, Holder, or even Chebyshev's inequality or convexity. And we will see other approaches which might fail at some point, but they can be, be successful. All right, so, well, the official solution, which was presented in the jury, so let me start with that. So the official solution was like this. So we show that A over the square root of A squared plus 8BC is greater or equal than, and now I'm going to put something like this, A to the power 4/3 over A. So we're going to have this. Now, the question is, you see, this feels kind of unnatural to do such a thing, and many people did not come up with this kind of a solution during the contest, like maybe very few. So usually you try this kind of approach, and, well, if you look at this expression, so I'm going to go a little bit in a, I don't want to delve too much into calculus, but if you look at this function as a 3-variable function, so you can look at this in this way. Right? And, well, of course, this expression, let's call it as homogeneous. And also it is symmetric, right? So now the question is how to come up with such a thing. So usually when you try to come up with, and how do you find this exponent, right? So usually when you consider this kind of function, or maybe you can consider part of it, so we usually try something like this. So a over the square root of a squared plus abc is greater or equal than, and we put here a to the power alpha over a to the power lambda, plus b to the lambda plus c to the lambda. And we're wondering, what is that lambda? So maybe you can try, you will see that if you look at this expression and you try to take a to go to 0, there is no way. The only option you have is that lambda is greater or equal than 1. So, sorry, less than 1. Greater or equal than 1. So if you try something like 1/2 or 1/3, this will not work. And the way you look at it, you can look at it in the following way. So basically, if you look at this function, if you just, okay, you take the derivative, so you can consider f, okay, let me consider g of a, b, c to be a over the square root of a squared plus abc minus a to the power lambda over a to the lambda plus b. So you can look at this function as a 3-variable function. So now I'm going a little bit beyond the, and if you compute the derivatives of this, which is not, it's a little bit complicated, so I don't want to get into details at the moment. So if you compute the partial derivatives with respect to a, let's say at 1, 1, 1, and you set them equal to each other, and you will find exactly the reason why, and you set them equal to each other to 0, then you will find exactly that that constant lambda is 4/3. And now, once you have this inequality in place, you just need to do some algebra here. For example, I think this is not hard to prove. So once you have this inequality, the only thing you need to do is just to do these substitutions. And then everything else will just become an AM-GM. So, and then you'll use the AM-GM inequality to anyway, I'm not going to go into details, computational details at the moment. So that was the official approach. At that time, it seemed a little bit unnatural to have this kind of approach to such an inequality. So that's why many contestants came up with this solution. But the more natural way to do this is to look at it, and once you see this kind of square roots, well, it's natural to think of Cauchy-Schwarz inequality. So let's say another solution to look at this is using Cauchy-Schwarz. I think this is the most natural solution to this. So if we look at this, so the way to look at it is by using Cauchy-Schwarz in this way. And once we do this, so once we do this, we're left to prove with a following inequality. So we're left to show that we have an inequality like this. So the sum of a times the square root of a squared plus 8bc is less or equal than the sum of a squared. So sum of a, everything squared. Okay, here also it's another temptation. So you can use Cauchy-Schwarz in actually 2 ways. First, you'll be tempted to put this guy inside the square root, right? All of it, but that will be, let me put it, you'll go into a danger zone because there is no way out of this. So a much wiser approach will be to just break this guy into 2 square roots, and then you use Cauchy-Schwarz in the following way. So you can have it like this. So the sum of A times the square root of A. So you can use it in this way. And I think at this point, once we use the Cauchy-Schwarz inequality, again, this would be less or equal than sum of A, the 1/2 times the sum of, when we add them up, it's sum of A cubed plus 24 ABC to the 1/2. In any case, now the problem is finished, since the only thing we need to prove, so we are left to show that, and I think that the sum of A everything cubed is greater or equal than the sum of A cubed plus 24 ABC. Anyway, I think this is pretty easy to see here. So that is the approach. I think this is the most natural approach. And to my surprise, not many people gave this solution. And I will tell you afterwards what has been tried by many, many contestants at that IMO. So another approach to this inequality, we can also use Holder's inequality, not just Cauchy-Schwarz. In fact, Holder's inequality is very similar. The solution using Holder's inequality is very similar to this one because, well, it's just a Cauchy-Schwarz, but we don't need to do these 2 steps. So basically, one can write using Holder's inequality in the following way. So basically, I'm just going to write it like this. So it's the sum of A over the square root of A squared plus 8BC times the same. So we have, and this is greater or equal than, in fact, this shouldn't have any square root here. And this is greater or equal than, when you multiply all this, is the sum of A, everything cubed. And then guess what? It will end up just like here. So we'll end up with the same inequality to prove as this one here. So the Holder's inequality approach is much faster, but it's a little bit more tricky to see. So, and you, etc. You end up doing the same thing as in the previous solution. But okay, so, but suppose we don't have this kind of ideas, although it's kind of absurd to believe that you will not try to use Cauchy-Schwarz or Holder's inequality to solve a problem of this kind. But let's assume that you don't have this approach. So in this way, maybe you can look at this expression closely. And now I'm going to try the more complicated approaches. So these are, let's say, the easier ones. The more complicated approaches, you will see that are a little bit more difficult to handle. And in fact, let me just use the one that, since we looked at this expression, right, and we said that this is homogeneous, so basically, without loss of generality, I can assume that the product is 1. And in fact, by using this assumption, we can actually reduce the inequality to a much simpler one. So basically, let me just write it. So in this way, one can write that the sum of A over the square root of A squared plus ABC. So using this assumption, this would be, anyway, I'm just going to write it in this way. So it's a square root of a over the square root of a cubed plus 8. So it's greater or equal than 1. Well, you look at this, and now we have here only an a expression in a, b, c. And you'll be tempted to use maybe some kind of a convexity. But once you want to go on this approach, it might be a dangerous one, because you don't know if this function is convex on the entire domain, and we will see such an approach. So here, it will be wiser to perform some substitution to actually to make things look nicer, especially on the numerator. And the way we're going to do this is just going to use the substitutions. So we're going to use, let's say, x equals 2 over a, y equals 2 over b, and z equals 2 over c. And our inequality transforms into the following. So we, the problem reduces to, so we need to show that the sum of 1 over the square root of 1 plus x cubed is greater or equal than 1, provided that the product is 8. And now we did this substitution in a wise way, because I was trying to, I want to have 1 here so that I can use an identity. So basically, what I can do here, I can just break this into the product of, so we can have the following. So the square root of x plus 1 times x squared minus x plus 1. If we use the AM-GM, so the intention is to use the arithmetic geometric mean inequality here on the denominator. So this will be x squared plus 2 over 2. And now, once we have this, so we are left to show, and this is will be a very, so we are left to show with, so we are left to show that, okay, let me write like this. The sum of 2 over x squared plus 2 is greater or equal than 1, provided that, let's not forget our condition, x, y, z equals 8. But now, just if you do the computations here, this inequality will be equivalent with showing that x squared is greater or equal than 12. And now it's just the AM-GM. So this solution seems very simple, but actually it's a bit tricky, because you need to come up with this substitution. So for example, if you just denote x to be 1 over a, then you might have some trouble seeing this product decomposition here. So these are the, let's say, the easy solutions, the first easy 4 solutions. And maybe there will be a 5th one. And we said, usually when you have an inequality of this kind, you try to approach them in a very classical way. So we've tried, the AM-GM, Cauchy-Schwarz, Holder, but there's one inequality that's left, and maybe we can also try to use Chebyshev's inequality. And so I assume everybody knows Chebyshev's inequality. And the trick here is the following. So we need to look at the denominator there. And we look at this guy. So we look at a squared plus 8bc. So what we're going to do is just going to break this into the following way. So it's a squared plus 2bc times plus 6bc. And now this guy will be less or equal than sum of a squared plus 6bc. And let's just call this S. And now, what we're going to do is just we're going to use Chebyshev's inequality. So use Chebyshev's inequality to the triplets ABC and the other one will be 1 over the square root of S plus 6bc, 1 over the square root of x plus 6ca, and 1 over the square root of s plus 6ab. And after you do this, surprisingly, the inequality simplifies a lot. And basically, anyway, I won't get into the computations right now to lose more time with that. But basically, it will simplify. And the only thing you need to do is just to do some arithmetic geometric mean inequality. So in other words, it will be very similar to what we did in this solution. So it will end up to this kind of inequalities here. All right, so these are the solutions that are more, let's say, classical in some sense, but there are some others as well. And the other ones that are more, I would say, a little bit more complicated is the ones using convexity. There is also an approach using Jensen's inequality. Anyway, I don't. So another approach using Jensen's inequality, but this one will be a little bit, it's not obvious how to use Jensen's inequality. So basically, we would like to, okay, I'll explain to you what is the danger here. So, so we're trying to look, do you have a, that's okay. So the danger of using, we will use the weighted version of the Jensen's inequality. It's okay, okay. And all right. So we look at this function. So another approach, let's say the sixth approach, is using Jensen's inequality. But we're going to use it in a following way. So we look at this. So basically, we'll try to rewrite our inequality. And we actually want to look at this function, 1 over the square root of x. So let's consider f defined in this way. F of x is 1 over the square root of x. And anyway, one can show that this function is convex on 0 infinity. And now, the way we're going to use it, without loss of generality, right, we can also assume that the sum is 1. And the way we're going to use it is in the following way. So we're going to write our inequality as follows. So the sum of A times f of A squared plus 8bc. And once we apply the weighted version of Jensen's inequality, this will be greater or equal than f of the sum of A times A squared plus 8bc, which is nothing else than f of the sum of A cubed plus 24abc. So now, basically the inequality is more or less over, because also the function is decreasing as well. And one can use the fact when this is decreasing, so basically using the fact that a cubed, the sum of a cubed plus 24 ABC is less or equal than this. So the symmetric sum of a squared b plus 6 ABC. So once we have this, and using the fact that it's decreasing, the inequality follows again. Basically, the same thing as solution 2. OK. So this was the approach, the first approach using Jensen's inequality. And this was a lucky one. But what if we don't have the idea of using the weighted version of Jensen's inequality, and we want to use it directly? You see that that's actually a danger zone. And I'll explain immediately why is that. So let me just say, OK. So another approach using convexity. And many people tried this, actually. For some reason. It's actually very tricky. So let's rewrite our inequality in the following way. So the inequality can be written as, so we can write it in this way. And now what we're going to do is just we're going to denote this. Let BC over A squared to be A and so on, and the analogs. So we want to show that. That the sum of 1 over the square root of 1 plus 8a is greater or equal than 1, right? Provided that ABC, the product is 1. OK. So this inequality, actually, we reduce our problem to this inequality. And many people try to do that. In fact, it can be done in an elementary way as well. A little bit more computation. We'll discuss this. So in other words, that problem is equivalent to this one. So many people tried this approach. And a dangerous way to do this is the following, because this could be a real trap, and you have to get out of it. So what many people tried was the following. So basically, they look at this function. They say, OK, this is not convex the way it looks. But if I do maybe a substitution, a nice one, maybe I could make it look convex. So what they try to do is to take this a to be e to some exponential, so e to the power x and so on. So in this way, you can rewrite your inequality in the following way. So if we denote a to be e to the a to be e to the x, e to the y, and c to be e to the z, we have to show that this inequality holds true. So 1 over 1 plus 8 e to the power x greater or equal than 1 with the sum 0. The problem is, when you look at this function here, so when you look at this function, it's not convex on the entire domain of definition. So this function is concave on negative infinity, negative log 4, and convex on negative log 4 infinity. So, and now you can still get out of here, but you need to consider 3 cases. So this is a little bit more complicated to handle. But the thing is that this inequality actually can be proven without using convexity. Actually, I'm not sure how much time I have. 10 minutes. OK. So you can, like I said, you can, if you don't want, if this convexity approach will lead you to this, which seemed to be no way, that you don't have any way out of here, well, what you can do is just to look at this inequality and try to, so another approach could be is to reduce this inequality even more. And we can do that in the following way. So what we can do is just to use the following substitutions. So basically, 1 over 1 plus 8a, the square root of 8a is x, 1 over, and the analogs. And then the problem becomes the following. So we need to show that. So the problem is equivalent with showing that the sum, so the sum of x is greater or equal than 1, provided that so once we do here this computation, computations here, so the condition will become that the product of 1 minus x squared is 512 product of x squared. And we can reduce it once more. And here again, it's once again, this is a dangerous terrain to go into, because we kind of need to handle these powers here. But we can do this, but we need to be very careful about it. And the way we do this is in a very tricky way. But the only thing we need here is just the arithmetic geometric mean inequality. So if we assume by contradiction that, so assume by contradiction that the sum of x is strictly less than 1. And now what we're going to do is we're going to use this condition here. So this guy here is 1 minus x times 1 plus x. So basically, what we're going to do is that this implies that 1 minus x is greater than 1 y plus z. And then what we're going to do is after we use AM-GM, so using AM-GM inequality, we'll get the following. So we will get that 1 minus x squared, using AM-GM and this condition, this will be greater than 8 of the 4th root of x squared y cubed z cubed. And then using the analogs and multiplying them, this will contradict exactly our hypothesis. So this is another way of doing this, another approach. Also, there are some other solutions to this inequality, which are way more computational than this one, and I don't want to get into that. Just I want to make one more comment about this thing here. In fact, here, so like I said, many people try to try this approach, and you can still do it, but like I said, you need to consider three cases here. When all of them are, when x, y, and z are in this interval, there is no problem, so we can apply Jensen's directly. But in the other two cases, you have to be very careful with this function. So you look at its inflection point, so it's a little bit more analytic, so you use calculus. Okay, I think that's what I had to say. I'll stop here. Thank you. If you have any questions.
Oui.
I have a question about solution number 4. At the end, we needed to prove that sum of 2 divided by x squared plus 2 is greater or equal than 1. And you said that it's equivalent to sum of x squared is greater or equal than 1. And why is this equivalent?
Wait, well, the solution 4 was the one using Chebyshev's, right?
The one before that.
The one before that, let me see. I don't recall exactly from the top of my head.
Substitution 2 over a as x.
2 over a, yes. Okay, I remember. So basically, you say, so we ended up, if I remember correctly, with this kind, right? This inequality here. 1, right?
Yes.
And then I said that this will be equivalent with this, right? You just do the computations here, you know, eliminate the denominators and everything. So
just multiplying by denominators?
Yes.
Okay.
Because the computations are easier here to do so. So once you do this, you will end up with this.
Okay, thank you.
If you have other questions. Okay.
So for that approach with 1 over square root of 1 plus 8 ex greater or equal than 1. Technically, when you have a function that is concave on some part and then convex on the other, you can...
you mean this this approach?
Yes. You can get in the end that all on the concave part, the variables are getting further away from each other, and on the convex one, they must be approached.
Exactly.
So you get that all but 1, so in this case 2, can be taken to be equal.
Exactly.
Can you finish using this x equals y and z equals minus 2x? Does this work?
Yes, it works actually.
Okay.
Actually, that's the way out. So basically, you'll end up with the function something like you take this function f of x plus f of negative x over 2, something like this, and study the variation of that function. And in that case, you need to show that it's greater than 1 or something like that. But yeah, this approach actually, it works the way you said. Okay.
Okay, maybe a hard question to answer, but like some of the solutions are of course elegant, some others were ugly. And then you also have the ones who fail. But how to know, or like how do you feel that like an approach which might be computation intensive will lead to something, and when can you feel like, okay, like this goes nowhere, like there is somewhere a trade-off, and of course you may guess wrong?
Well, in this case, okay, my opinion will be a little bit biased since I've dealt with inequalities a little bit more than usual. Since I look at this inequality, it's symmetric, it looks very nice, so I suspect the classical approach should be successful. So I don't see any point of getting into that kind of computational approach, especially during the competition. But also, it depends. If you are good with calculations and computations and everything like that, you can go in that route. But I prefer not to. I'm more for elegant solutions.
Who is not?
Even though if they're tricky. Yeah, any other questions?
If there's no questions, let's thank Theda again.
Okay, thank you.